This is the first slot of atmospheric aerosol particles monitoring and source identification. I am very pleased to present today's speakers. The first presentation is entitled Direct Measurement of Air Particulate Matter Filter Elemental Composition and will be presented by Paola Cirelli. Please.
Good morning to everyone. I am Paola Cirelli, PhD student at the University of Brescia. My research deals with air pollution challenges. This presentation consists of a brief introduction about the problem of air pollution. Then I will describe a new approach for the analysis of air filters with TXR spectrometers, together with the sample preparation procedure. Then I will show you the results of the calibration procedure performed with different TXRF spectrometers. Air pollution is a global threat that determines large impacts on human health and ecosystems. Currently, it is the most important environmental risk to human health. Air pollution is a major cause of premature death and disease, causing around 400,000 premature deaths per year in Europe. In particular, heart disease and stroke are the most common reasons for premature death attributable to air pollution. The most serious pollutants in terms of harms to human health are particulate matter, nitrogen dioxide, and ozone. Sources of particulate matter are several and include energy production and distribution, transport, industries, and waste. The chemical composition of particulate matter includes heavy metals. Despite the decrease in emissions of toxic metals into the air in the last decade, the long-term risk to human health and ecosystems still remain as a result of the accumulation of metals in soils from past anthropogenic emissions. An increased awareness of the effect and costs of air pollution has led Europe to take action. The European Union has been working for decades to improve air quality by controlling emissions of harmful substances into the atmosphere. With the Ambient Air Quality Directive of 2008, the European Union demanded that member states adopt and implement air quality plan. The directive imposed limit values for the concentration of pollutant for the protection of health. But how can we determine the concentration of a specific pollutant in the air? According to the European norm 14902 of 2005, air pollution can be evaluated analyzing air filters that collect air particulate matter. The normative establishes that the reference methods that can be used to determine the chemical composition of air filters are ICP-MS and GFAAS. These techniques, however, are time-consuming and require filter digestion with toxic acids, with the consequent production of dangerous waste. The question is it possible to analyze directly the filter and obtain a quantitative elemental composition without destroying it? The answer is yes, it is possible. Recent studies have shown that it is possible to exploit total reflection X-ray fluorescence spectrometers for the direct quantitative analysis of air filters. Total reflection X-ray fluorescence analysis shares the same principles of classic X-ray fluorescence. When the sample is hit by an X-ray, an electron from the inner orbital shell of the atom is expelled. The ejected electrons leave behind vacancies, making the atom unstable. Electrons from outer electron shells fill the resultant voids, emitting a fluorescent radiation that is specific for the atomic spaces involved and allow to obtain a quantitative and qualitative information about the elemental composition of the sample. The XRF technique is developed from the classic energy dispersive X-ray fluorescence, and it differs from it in the geometry of the source sample detector system. The total reflection condition is obtained when the incident beam is completely reflected by the surface of the sample, and this occurs when the X-ray beam is almost parallel to the sample, and not at 45 degrees like in conventional XRF. In this way, a higher sensitivity is reached. Matrix effects are negligible. Compared to conventional XRF, the XRF allows to measure trace levels of elements in the ppb range. The XRF sample preparation is fast and easy, and this technique allows to measure all the elements simultaneously. The XRF allows to obtain qualitative and quantitative information about the composition of a sample. This technique can be employed in the environmental field for several applications, for example, for the analysis of groundwater, tape water, waste, soils, and biomonitors. Thanks to its higher sensitivity, it is possible to determine the The XRF is also suitable for the direct analysis of air filters, prepared according to the procedure called Smart Store. And this is the core of my research. In order to perform a direct quantitative analysis of air filters, the sample is prepared according to the Smart Store procedure that allows a direct analysis of the sample without any chemical pretreatment. The sample is then analyzed with commercially available TXRF spectrometers. In our case, we use the commercial Horizon TXRF spectrometer by GNR, equipped with a molybdenum X-ray tube, and a custom-made Wobby Compact by Atom Institute, equipped with a rhodium X-ray tube. The spectra obtained from the measurement of the sample are analyzed to extract the fluorescence intensity of the investigated element. These data are compared to calibration lines built for each element of interest and specific for an instrument. In this way, the elemental quantification is obtained. But what is the Smart Store procedure? Smart Store is a tool developed by Smart Solution, a spin-off company of the University of Brescia. The most common filters used to sample air particulate matter are Teflon filters that are equipped with a plastic ring to stretch the filter and avoid crushing. This plastic ring, however, impedes the passage of the X-ray beam when the filter is analyzed with a TXRF instrumentation. The Smart Store procedure consists in sandwiching the filter between two thin polymeric sheets. The filter is then cut in a disc of 30 mm diameter, equal to the dimension of the sample carrier. By cutting the filter, the polymeric ring that stretches the filter is removed, so that it is possible to measure it with TXRF spectrometers. The obtained sample can be easily handled, and the loss of material is avoided, and it can be stuck onto a carrier to be measured. This procedure has several advantages. With respect to the conventional methods for filter analysis, the Smart Store system allows to shorten the sample preparation time. The sample is not destroyed during the procedure, so it can be analyzed several times, also with different instrumentations. This system is user-friendly, as the operator can be anyone and not necessarily a chemist. The Smart Store is synchronized because all the results of the analysis can be stored in the Smart Store app, and the data can be accessed thanks to a QR code generated for each sample. And it is also sustainable because no toxic reagents are needed. The idea of the Smart Store is dated back to more than 10 years ago. In 2008, the patent application failed. In 2014, the first step-by-step manual procedure was created. The project was presented to the first edition of DAS and the following year at the Expo for food application. In 2018, a preliminary working item was presented at the ISO community with the aim to validate the analysis of air filters with commercial TXRF spectrometers, and this is still under development. Finally, this year, the new engineered prototype has been created. In our study, we took into account lead-loaded reference samples provided by the Air Quality Research Center at the University of California, Davis. Samples consist in 4 mono-lead samples, 1 multi-element sample, and a blank. The mass loading of the samples range from 0.028 up to 10.2 microgram over square centimeter. Lead salt was used for generating aerosol collected on Teflon filters, with loading close to the European limit values for lead in atmospheric aerosol. All the filters were prepared according to the smart store procedure. In the picture, we can see the spectrum of one of the lead-loaded reference sample, taken with 2 spectrometers equipped with different excitation sources, 1 molybdenum and 1 rhodium. The 2 peaks correspond to the L-alpha and L-beta emission lines of lead. Reference samples were used to build a calibration line that can be then used for the quantification of real air filters. Calibration lines can be built applying an empirical approach or a theoretical approach. The empirical one consists in establishing a direct relationship between the known concentration of an element and the detected fluorescence intensity. On the other hand, the theoretical approach is based on the equation of the fluorescence net intensity of an element. With both methods, a calibration line for a specific element is obtained, with a range of linearity defined by a statistical analysis. Both the approaches require the use of reference materials, of filters with known mass deposition. Therefore, reference samples of each element of environmental interest, such as nickel, arsenic, and cadmium, are needed to build calibration lines. Here, we can see the result of the measurements performed with a custom-made spectrometer equipped with a rhodium tube and with the commercial TXRF spectrometer of a GNR equipped with a molybdenum X-ray tube. The spectra obtained from the measurement of reference samples were analyzed, and the net integrated intensity of lead was extracted, considering both L-alpha and L-beta peaks. An empirical approach was first adopted. The obtained values of lead intensity were plotted in correspondence of the known mass loading of the filters. With the rhodium spectrometer, a calibration line with a good confidence was obtained, and this is stressed by a high coefficient of determination. For the molybdenum spectrometer, an absorption phenomena was observed, and the sample with the higher mass deposition was excluded from the linear range. With both the spectrometers, a very low detection limit was reached, well below the threshold limit of lead in air for air quality. The data obtained with the molybdenum TXRF spectrometer were analyzed also with a theoretical approach to evaluate if it was possible to extend the calibration line to all the reference samples. This approach takes into account matrix absorption contribution that are mass dependent. Therefore, considering the different mass loading of the sample, it was possible to calculate the absorption contribution and correlate it to the detected fluorescence intensity of each sample. In this way, it was possible to extend the range of linearity to all the reference samples in study, up to 10.2 microgram over a square centimeter. Even considering the empirical approach that allows to build a calibration line with a restricted range, the method can be considered satisfactory from the point of view of environmental monitoring, because the European Union established a lead concentration limit in air equal to 0.5 microgram over a cubic meter, that correspond to a lead mass deposition of 0.4 microgram over square centimeter on the filter. And this value is largely included in the linear range of the method. The data of the calibration are then stored in the Smart Store app. In this way, when a real air filter is analyzed, the elemental quantification can be immediately obtained thanks to the calibration specific for each spectrometer. Up to now, we have tested only lead reference samples, and now we are moving to implement calibration lines with all the other elements of environmental interest. Concluding, the Smart Store preparation procedure is suitable for air particulate matter filter analysis with commercial TXRF spectrometers. The direct analysis of air filters is possible, applying an empirical or a theoretical calibration approach. The limits of detection obtained with the spectrometers with the two different sources are well below the threshold established by European Union for air quality monitoring. Therefore, the method is satisfactory from an environmental point of view. Our goal for the future is to realize reference materials for other elements of environmental interest. We are now moving to the study of model samples with different geometry to assess matrix effect, and we are evaluating the size distribution of the nebulized particles in order to mimic the particulate matter distribution. We would like to implement a system that allows to generate an aerosol which is fully conveyed on the filter with no dispersion, so to allow a correct quantification. Finally, I would like to thank all the team of the Chem4Tech Lab at the University of Brescia. Then I would like to thank Dr. Giacomo Siviero, Professor Tsuji, and Diana for their help and suggestion, and the Cost-Action and Force TXRF. Thank you for your attention.
Many thanks, Paola. And are any question in the room?
No.
No, I don't see question for Paola in chat box, but I have just two curiosity, Paola. Is X-ray fluorescence useful for low atomic number elements? And what are the limits with respect to the mass of the PM, if there are, of course? Finally, is possible to use another kind of filter?
Well, first of all, about the instrumentation.
Okay.
The TXRF spectrometer that we used are commercially available spectrometer that works in air, so they are not suitable for low mass, low atomic number elements. If in some laboratories there are instruments that works without air in a void, and that kind of instrument are also able to detect that kind of elements. And of course, we analyze in our case study Teflon filters, but this procedure can be applied also to other types of filters. We perform other experiments also with nylon filters, for example.
Okay, thanks. Many thanks again. Okay, the next presentation will be given by Chen Weidong, who will present us a work on photoacoustic spectroscopy for filter-free measurement of aerosol particles light absorption.
Hello everyone, I'm Wang from University de Haute-Côte in France. I present here our new progress in the photoacoustic spectroscopy for field-free measurement of aerosol particle light absorption. I will introduce my work from the four parts: motivation, introduction, the state of the art techniques and change, and field-free direct measurement of aerosol particle by photoacoustic spectroscopy. In the lab measurement of black carbon, volcanic ash, secondary organic aerosol, and a field measurement of ambient particulate matter, and then summary and perspective. For the motivation and introduction, nowadays, the impact of aerosols on the climate change has drawn all the society attention. The radiative forcing is used to evaluate this impact, but the uncertainty in the aerosol radiative forcing is very large, equals to its magnitude, as shown in this figure from the IPCC. The measurement uncertainty is very large, equals to its magnitude, and the uncertainty in the estimate of aerosol radiation forcing is caused by the simulation model, remotely sensing data, and ground-based measurement. Our work is focused on the ground-based measurement for providing more accurate measurement of aerosol optical properties. But what kind of information should we provide? To study the health effect, the mass concentration is very important. It can be determined by the mass absorption efficiency and the absorption coefficient. To study the climate effect, the aerosol single scattering albedo is very important, which can be determined by the scattering and extinction coefficient. And the aerosol complex refractive index can be determined by the extinction coefficient. Therefore, we can provide the accurate measurement of aerosol optical properties, including absorption, scattering, and extinction coefficient. For the state-of-the-art techniques and changes, nowadays, many methods have been developed for the measurement of optical properties of aerosol, including extinction, scattering, and absorption. For the extinction coefficient measurement, the multiple cell and the cavity-enhanced spectroscopy, including CRDS, BBCS, and CUPS, are widely used due to their wide spectral range, high sensitivity, broadband, and low cost, respectively. Nephelometer is used for the measurement of scattering, and our work focuses on the absorption coefficient measurement. Normally, the filter-based technique are widely used for absorption coefficient due to its low cost and simple structure. The difference method is based on the measurement of extinction and scattering. Then the difference is absorption coefficient, but this method has light uncertainty when the absorption is very small. Photoacoustic spectroscopy is the field-free direct measurement. We talk about the field-free because in the common technique for aerosol absorption, field-based method is used the filter to collect particle, but the filter will influence the measurement of light absorption, and the light scattering from the filter will affect the interaction of the light and absorption, and also the filter loading will modify the aerosol microphysical and optical properties. Therefore, the measurement uncertainty is around 20 to 35%. But the photoacoustic spectroscopy can measure the aerosol in a natural span with a measurement uncertainty of 5 to 10% without using filter. The photoacoustic spectroscopy was founded by Burr in 1880 years, and this method is based on the light absorption of modulated light by species, including the gas or aerosol, and this light absorption will result the heating of the illuminated volume and the thermal expansion. When the light is modulated, the thermal expansion will result the generation of a pressure wave, which is an acoustic signal. Then this method will use the microphone or glass tuning fork to measure the acoustic signal. The photoacoustic spectroscopy is frequency independent with light absorption in all spectrum, and is also a background-free method. Another important parameter for the particle is the absorption angstrom exponent. This parameter, AE, describes the dependence of absorption coefficients on different wavelengths for different aerosol composition. The AE has different value. For the black carbon, this value is around 1, and for the organic carbon, this value is from 2 to 9. Therefore, multivalence measurement of aerosol absorption can be used to identify the aerosol composition. For the measurement per symbol of photoacoustic spectroscopy, the photoacoustic signal depends on the excitation light power, the microphone sensitivity, and the photoacoustic cell constant that can be determined by a calibration, and also the absorption coefficient that is related to the aerosol mass absorption efficiency and aerosol mass concentration. Then the background photoacoustic noise can be determined in the lab using nitrogen. Therefore, with the measured photoacoustic signal and the known concentration, the particle absorption coefficient can be determined. And this figure here shows the developed photoacoustic instrument with three wavelengths at 444, 532, and 616 nanometer. And the three dot layers are coupled together and pass through a photoacoustic cell. The photoacoustic cell is composed of a cylindrical resonator with a length of 23 nanometer and a diameter of 6 millimeter. The light is modulated at 6,000 Hz, and this modulation frequency is the fundamental resonant frequency of a photoacoustic cell. And 4 microphones are installed in the photoacoustic cell to measure the acoustic signal. And the bottom of the instrument is all the diode laser controller and power supply and other electric device. And this figure has shown the developed three wavelength photoacoustic instruments. And in the lab measurement, we measured the light absorption of the black carbon and volcanic ash. And this figure has shown the system schematic of the measurement of black carbon and volcanic ash. The up is the developed photoacoustic spectrophone. Before measurement, the photoacoustic spectrophone should be calibrated using a known concentration of NO2 to determine the photoacoustic cell constant. And the bottom of this figure has shows a homemade aerosol particle generator. All particles were put in the test tube, and we use a magnetic stir to rising up the particle, and a nitrogen flow as carrier gas will send all particles into a buffer volume, and the particle channel will divide into two channels. One channel connects to a CPC for measuring number concentration, and the other channel will pass through the photoacoustic cell for measuring the absorption coefficient, and connecting with the SMPS to measure the mass concentration and particle size distribution. And this figure shows the measurement result of black carbon. The black carbon is a conventional graphite from Eldridge with size less than 500 nanometer. And this figure shows the determined mass absorption efficiency at different wavelengths. The determined mass absorption efficiency are well consistent with the previous reference. And the simulated AAE is around 0.96. It will grow with the black carbon, the typical value of AAE. And this slide shows the measurement results of volcanic ash. The volcanic ash is from this volcano located in Iceland, and the volcanic ash is from the eruption in 2010 year. This sample was provided by the University of Brussels, and this figure shows the determined mass absorption coefficient. It will grow with the previous measurement reference, and the simulated AAE value is around 3. It indicates the volcanic ash contains abundant organic carbon. For the measurement of secondary organic aerosol measurement, and the SOA are produced from photolysis of 2-nitrogen in a chamber, and the 2-nitrogen was photolysed by the UV and visible light. In the chamber, an IBBCES instrument was installed to measure the particle extinction coefficient, and the NOx analyzer, SMPS, and the developed photoacoustic spectrum will connect with the chamber to monitor the photolysis process. And with the light on, the photolysis process continues and alerts start and alerts SOA are generated, and the mass concentration, the absorption coefficient, and the extinction coefficient were recorded in the time. And with the measured value, the mass absorption efficiency and extinction and scattering efficiency and the single scattering albedo were determined. And as shown in this figure, with the photolysis process continue, the mass absorption efficiency decrease, and the extinction and scattering, the mass extinction and scattering efficiency increase. This is due to the etching effect that degrade SOA to make SOA particle less absorbing. And this figure has shown a field measurement of a particle in a suburban area in Krneta in France. Our measurement site is an intersection of a circular overpass, and this field measurement was carried out using photoacoustic spectrum and a conventional accelerometer, and the measured error absorption coefficient at two wavelengths were compared, and a high linear regression of 0.93 was obtained. For summary and perspective, now we have developed a prototype of a multi-wavelength photoacoustic spectrometer at three wavelengths, 444, 532, and 660 nanometer. And this photoacoustic spectrum was validated by the determination of AAE of black carbon and volcanic ash, and the single scattering albedo of SOA, and a field test by intercomparison with the reference accelerometer was carried out, and good linear correlation has been obtained. For the future work, a novel black carbon analyzer for simultaneous measurement of extinction and absorption will be developed by combining IBBCS and photoacoustic spectrum. And these instruments will use a broadband laser source with a spectrum from 300 to 2000 nanometer. And then thanks very much for your attention. Thanks my colleague for the measurement area.
Thanks, Dr. Chen. And any question in the audience?
Question.
Okay, thanks.
Thank you for this informative presentation. My question has to do, what do you measure exactly? Because you haven't shown any raw data, and I wonder about the cavity resonances. How do you take the data? Can you explain in a few words what you do with gases and with aerosol?
Sorry, is Dr. Weidong on the line? No.
No, maybe no. No.
No. I'm sorry.
Okay.
Okay. Okay. Well, now we can move on the first presentation of the poster session with Jelena, Krneta, Nikolic, who will talk us about activity concentration of 200 2010 lead in aerosol in Serbia in the period of 2014 to 2020 and a comparison between results from urban and rural sampling stations. Please, Jelena.
Good day, everybody. My name is Jelena Krneta Nikolic, and I work at the Department of Radiation and Environmental Protection of the Institute of Nuclear Sciences Vinča in Belgrade, Serbia. I will now briefly present our paper where we have analyzed 7 years of measurement of lead-210 in aerosol in different locations in our country. Monitoring of radioactivity in aerosol is readily performed within the frame of environmental radioactivity monitoring in the Republic of Serbia. It provides information important for the preservation of the public health and the environment, and this kind of years now.
We have a problem.
Okay. Rosa?
Yes,
You hear me?
I can hear. And
Okay, okay. I can restart the presentation.
okay, thanks.
Just a moment.
Okay.
Sampling of aerosol is performed on different locations throughout the country for the purpose of environmental monitoring. Samples are collected using constant airflow pumps and filter papers that you can see on the picture on the left. Now you can briefly see the locations on the map. Filter papers are exchanged every 2 or 3 days, and monthly composite samples are ashed on 380 degrees centigrade. The remaining ash, containing only aerosol, is then measured on high-purity germanium detectors that you can see on the picture below, using standard gamma spectrometry method. Activity concentration of lead-210 in aerosol was determined according to the equation that you can see on your screen, where N over T is the number of detected photons in time unit, epsilon is the detection efficiency, P gamma is the probability of emission, and V is the air volume that passed through the pump. The activity concentration in all investigated samples showed temporal dependence, with the maxima in the winter and minima in the spring and summer of the year. The values obtained at measuring stations in the rural parts ranged from 0.051 to 2.9 millibecquerels in cubic meter, while for stations located in urban areas, it ranged from 0.125 to 3.3 millibecquerels in cubic meter. On these graphs, the first group represents results obtained at rural areas of the meteorological station at the Institute, Palić and Zlatibor. There were some outliers at Palić that are probably caused by the prevailing winds in the Vojvodina plain that are carrying sand from Deliblatska Peščara. On second group of graphs, we can see the results obtained at urban locations of cities Vranje, Zaječar, and Belgrade station Zeleno Brdo. As a conclusion of our investigation, we can say that all observed values of lead were of the order of magnitude of 10 to minus 3 to 10 to minus 4 becquerels per cubic meter, which is in accordance with the previous long-term measurements in Serbia and measurements in other countries of Europe. It is noticed that the activity concentration is slightly higher on the measuring stations located in the urban areas. Activity concentration of lead shows seasonality and depends not only on the microclimate conditions, such as temperature, humidity, wind speed and direction, and precipitation, but on the presence of the total lead in the air, and especially on the presence of the foliage, which is a good absorber of the aerosol. This kind of measurement is continuous and lasts for long periods of time. This large amount of data provides a large base of results for further analysis. Thank you for your attention. Good day, everybody. My name is Jelena Krneta Nikolic, and I work at the Department of Radiation.
Thanks, Jelena. Okay. Is Jelena online? Oh, okay, I can
Yes,
see.
here I am.
Okay.
Good day.
Any question in the room?
No.
No? Okay, there aren't questions in the chat. Okay, in the chat box. Jelena, just a curiosity, why is the concentration activity of the 210 lead greater in the urban area?
Well, it can be for different reasons, but mainly because of the pollution in which the total lead is, the amount of total lead is larger, and therefore the isotope 210 is, the concentration is larger. But it would need a much deeper analysis, or analysis of all 30 years of measurement that we have to confirm this hypothesis. This investigation is in course, is done as we speak. And also there is a resuspension from the soil. It seems that in rural areas, this, especially in our station, this resuspension is not so large as in comparison to the urban areas. So to speak, the lead can come from the air and also from the soil, from the ground. It is interesting that it is a little bit higher in urban areas, although we should expect in rural areas to be a lot more free soil. But as it seems, our stations are in the areas where there are no land, agricultural land. It is the stations are situated in the green areas where the foliage covers the ground and there is no large resuspension from the soil. But as I said, a larger investigation is on course.
Thanks. There is a question in the chat. Do you know if the concentration are monitored and they are similar in the rest of the region and neighboring countries?
To my knowledge, these values are similar to all the other values monitored in other countries, especially in our region. Of course, there is no reason to be different. We have not detected any special outliers except these 2 or 3 in Palić region, which are probably due to prevailing winds. We're all the same. All the results are the same as in region. Thank you.
Okay, thank you very nice for your very nice presentation. And okay, Rosa, let's proceed with the proceed with the presentation of the poster on a preliminary analysis of urban dust sample from the Ohio State University campus, Columbus, USA, given by Barry Lyons.
Yeah. Okay, Rosa.
Okay.
Here you are. Okay, present the next talk. Present the next talk. Yes, Barry Lyons.
I can hear. Please, can you repeat, please?
Can you present Barry Lyons' presentation?
Let's proceed with the presentation of the poster of a preliminary analysis of urban dust sample from the Ohio State University campus, Columbus, USA, given by Barry Lyons. It's okay now?
Yeah.
Thanks. No?
A moment. It's very slow. Yeah.
Hello, today I would like to present the results of Hello, today I would like to present the results of work done in our research lab by one of our undergraduate students, Ms. Rujan Deng. Rujan has been taking part in the STEP program, which is the second-year transformational experience program at The Ohio State University. STEP is a mentoring program that encourages increased interactions with faculty, staff, and students, and allows students the opportunity to engage in research activities and to develop research networks. As part of the STEP program, and as part of our group's ongoing research on environmental and urban geochemistry, Rujan has been focusing on measuring the composition and concentrations of dust and determining factors that affect dust composition and concentrations. Our research site was located on the Ohio State University campus. And here's a map of the campus here. OSU is located in the heart of Columbus, Ohio, a large Midwestern city with a population of about 900,000 people. The Ohio State University has approximately 60,000 students and approximately 35,000 faculty and staff. The study was conducted during the pandemic, so the population on campus during the time period of study was not typical. Rujan focused on collecting dust samples from some newly paved surfaces so that she had relatively clean areas to start working from. Samples were collected periodically over time, typically over a couple of weeks. Samples were weighed, and then she did some statistical analyses to determine the relationship between the mass of dust and factors such as temperature, wind speed, or rainfall. We found that in general, the mass of dust was negatively correlated with wind speed, and we saw a positive relationship at one site between the mass of dust and the timing of antecedent rainfall. Several of the larger samples were analyzed by X-ray diffraction to determine mineralogy, and we found that the samples were predominantly dominated by quartz and feldspars and dolomite and calcite, which was expected based on the local lithology. But we also found that several of the samples had large amounts of anhydrite in them, which suggests that we're probably getting some dust either from degraded concrete or from some building material. We also analyzed the samples by both light and electron microscopy, and you can see some of the images here. These are some SEM images, and as well as some light microscope images. And the SEM image was consistent with the results that we got by X-ray diffraction. So lots of quartz and feldspar. Some of these phases here that look brighter in the backscattered detector images are iron oxyhydroxides. We also saw these rounded phases, which we think are probably fly ash, probably from the degraded concrete. And then we saw things that look darker in the SEM images. So things like these little filaments here and these filaments over here. And at first we thought these were predominantly organic matter, probably something natural. But when we looked at these materials in the light microscope, we saw that a lot of these were really brightly colored. So there were these long filaments, on the order of, several hundred microns long and a few microns in size, and they're probably microplastics. And we found them in just about every sample that we looked at. We also saw other organic matter. We saw bits of leaves. We saw things that looked like bits of stem, and things that looked like, bits of kind of woody materials. And so our results so far, it's a little bit hard to determine the major factors controlling the distribution of the dust. The SEM and X-ray diffraction analysis show that most of the material appears to be, rock and mineral phases, as well as, bits of woody material or bits of soil. And we did find microplastics in just about every sample that we looked at.
I think it is stopped.
Many thanks. And are any question in the room?
No.
No? Neither in the chat. Okay, thanks. And the next poster will be presented in person, I think, by Davide Ciniglia, who will talk to us about LIBS and TXRF measurement for metals concentration analysis in aerosols. Is it present?
Yes.
Okay.
Let's see here. I don't know what's happened. I don't know. Okay. It's you. Yes. You can start.
So thank you for letting me present this work. I'm a PhD student of the University of Brescia, and this project is co-founded from CNR and the company TCR Tecora. So the main part of the project is the study of the emission of metals aerosol at the stack of chimneys of industries and incinerators. And the main technique which I study is the laser-induced breakdown spectroscopy, which has some interesting characteristics, which is to be able to make real-time measurements. It has no sample preparation and has multi-elemental analysis. And as part of the work, I will present the part connected to the filter collection, because in the instrument there is also a backup filter of collection the produced aerosol, and these filters could be analyzed with the TXRF. Which has different advantages, which could be always multi-elemental analysis, but better low detection limits. And so the instrument could be useful for prepare reference filters to be used with TXRF. So the instrument consists in the principal part, which is the central one, which is the nebulization line through which the metals aerosol are produced. And there is the first chamber in which the LIBS measurements are carried out, and after there is a backup filter holder through which aerosol is collected and could be analyzed with TXRF. In these studies, I analyzed simultaneously copper, lead, and nickel in two different sets of measurements. The first one were 5 measurements at the same with the same deposition collection time, which permitted to analyze the stability of the production of aerosol, and another one to for filters at 4 different collection times. So here we can see in the first two graphs in the first column, this cluster represents the LIBS signal of the 3 different metals analyzed, and we can see that the signals are quite stable both in the repetition of measurements at the same time and both in different time measurement. So it reflects the stability of the aerosol production, which is could be also seen with the last graph, which is the mass deposited on filters measured with weighting the filters. In the central part, we have the first TXRF analysis, which aren't quantitative because there isn't the presence of the internal standard of calibration. So one aim of the project is to add this internal standard calibration. So in this work, we propose a reliable tool for prepare these standard filters, and LIBS was an interesting tool to monitor the production of the metals aerosol. So from the LIBS measurement, we see the stability in the signal, so the stability in the aerosol production, and therefore with the TXRF, we see the stability in the collection time. Because the percentage composition of filters remain keep stable in time and in repetition measurements. So the future work is to employ an internal standard for quantitative TXRF measurements. Thank you for your attention.
Thank you. Many thanks, Davide. And any question in the audience? No? No question? No. Just one.
Just,
Okay.
maybe
Okay.
this question from the chat.
No, sorry, Davide. I know if this approach is possible to useful for finer fraction of PM, for example, PM1, PM.
Well, the nebulization system that we use now is nominally from factory standard around 300 nanometers particles. So I think it's useful for finest particles.
Okay.
Less than 1 p.m.
Okay, then. Thank you. Bye. No.
Maybe there is
Okay.
in the chat, maybe.
No, in chat. Okay. No. Sorry, there is a question. Sorry, if I missed the information, what type of filter did you use? Yes, yes.
Yes, we used Teflon filters of 47 millimeters of diameter, so standard PTFE filters.
What type?
PTFE filters.
PTF.
Yes.
Okay, thanks.
Thank you.
Thank you again. The last work of the session will be presented by Antonio Lettino, who will talk about morphological features and elemental composition of PM1 aerosol particles inside on natural and anthropic sources.
In this talk, I will present the preliminary results on morphological feature and elemental composition on fine aerosol particle PM1 to identify the possible contribution of anthropogenics and natural sources on both local and long-range transport in the Egri Valley in the Basilicata region, southern Italy. The Agri Valley hosts the largest European onshore reservoir and one of the largest oil-gas pretreatment plants in anthropized area. In this plant, oil stabilization and gas conditioning are performed, implying continuous particulate emission in atmosphere. Data shown in this study refer to measurement of PM1 daily mass concentration of a fine aerosol particle between July 2017 and January 2018 by using a low-volume gravimetric sampler. 5 samples were selected for field emission scanning electron microscope observations that have included morphological and elemental analysis of single aerosol particle. As shown in the slide, the daily average level of PM1 mass concentration ranging from 3 to 19 ppm, with a mean value of 5 ppm. Such values are generally comparable with those found in other industrial areas. Regarding the FSM observation, 5 samples were selected considering different PM1 mass concentration, higher and lowest, and meteorological conditions, for example, no rain, no strong wind. In detail, about 300 particles for each of 5 filters chosen were manually analyzed using 15,000 magnification. Based on morphological and chemical characteristics, investigated particles were classified into 10 classes and 7 groups that include alumosilicate, quartz, calcium-magnesium carbonates, sulfur-rich particle, mixed particle, metal particle, and particle with low element, lighter than sodium. The results show that the sources make a different contribution to the PM1 mass concentration collected. In particular, as regards the sample with the highest PM1 mass concentration, some analyses have indicated the provenances from 3 different sources. The July 30 sample with the highest mass concentration shows high content of particles rich in sulfur and potassium, along with charbol coated with sulfur compound that may have originated from biomass burning. Regarding the other sample with higher mass concentration, August 28 and November 22 are characterized by the presence of rich sulfur particles and agglomerate soot, suggesting an industrial source, while for the August 20, a high percentage of aluminosilicate and gypsum particles indicate a Saharan dust contribution to the PM1. On the contrary, in the sample with the lowest mass concentration, the particles are mainly related to the phases with low atomic number element, referable to ammonium nitrates, fresh soot, and phases of an organic and/or biogenic nature, considered representative of the background environment. Many thanks for your attention.
Thanks, Antonio. Any question in the room?
No, nothing.
No. No in the chat. No. I would like to thank all the participants in the session for their very interesting contribution. The session is over, but the meeting resumes after the break. Thanks you all again. No, there is a question. Okay.
No question.
No.
It's not a question. It's a communication for the people that lose the Oriol Ishido talk. We upload it on YouTube, so people that lost this talk can give now a look at this presentation. Please note that on the program on the website, it has been reported that the session, the talk by Daniel Lax has been withdrawn by the author, and therefore the presentation, the talk that will be given by Chaofan Li has been moved to 4:30. So you have a long coffee break. Enjoy this coffee. See you later.